So, hello everyone, a very good morning to all of you, dear authors and all the invited guests. A very warm welcome to the technical session 8C. Myself Yashita, and I'll be your moderator for this session. I'll make sure everything runs smoothly. So, on behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you all to the 11th International Conference on Information and Communication Technology for Intelligent Systems. The 11th edition of the conference is being organized in a hybrid mode. The physical event is being held today in Bangkok, while the virtual sessions are being conducted via Zoom from 9th to 11th April 2026, while people from all over India as well as many from other countries are present with us today. I hope you all will enjoy today's insightful, knowledgeable, and interactive sessions. So, in this session, we will be having 10 presentations. Each presenter will be given 10 minutes for presentation, followed by 2 to 3 minutes for question and answers. I will give a gentle reminder to everybody at the 9-minute mark just to help everyone stay on track. Also, a small request to all the participants that please stay connected with us till the closing remarks. We promise this session will be worth it. So, if you have any queries or updates, feel free to drop them in the chat box anytime. So, before we begin with the session, I would like to introduce you all to our esteemed session chair, Dr. Virendra Kumar Dhotre. Sir, welcome to the session.
Thank you. And sorry, I'm bit late. Yeah,
That's
thank
fine.
you. Thank you.
He is Associate Dean of Academics at the Vishwakarma Institute of Technology in Pune. His research focuses on artificial intelligence, machine learning, the Internet of Things, and the optimization of data stream classification systems. He is actively involved in academic leadership, teaching, research, and curriculum development in advanced computing domains. So, sir, would you like to give some welcome remarks to everybody for today's session?
Hello, am I
Yes,
audible?
sir.
Yeah.
Yes, yes.
Good morning, everyone. First of all, I'm thankful that I've given this opportunity as act as a session chair, and I suggest participants that focus and you can say that you can put in forward your research, whatever your task you are done, and it will be well structured, organized, and well directed, so that we can go ahead with new innovations and new technologies. And all the best for everyone. Thank you. Thank you.
Okay, thank you so much, sir. So, I would like to invite our first presenter for today, Shailaja P. Are you there in the meeting, Shailaja? Let me check once. Okay, she is not there, so we'll proceed with our next presenter. So, next we have Gudivada Krishna Prakash. Are you there?
Yes, ma'am. Am I audible?
Yes, you're audible. Are you ready with the presentation?
Yes, ma'am.
Yes, so he is here to present his work titled as a secure and decentralized framework for threshold-based encrypted image sharing using blockchain and IPFS. So I'll stop sharing my screen. You can start presenting. So it's a humble request to all the participants that you have to finish the presentation within 8 to 9 minutes strictly and 1 to 2 minutes time for the question and answers by the session share or anyone from the meeting. Yes, so you can start.
Good morning, respected judges, professors, and fellow participants. Myself, Krishna Prakash from Department of ACSC, Vignan University. Today, we are living in a world where sensitive images like medical records, personal data, and confidential information are shared every second. But the question is, are they really secure? Uh, our team addresses this critical problem by proposing a secure and decentralized framework for image sharing using encryption, blockchain, and IPFS. Abstract. The sharing of images in decentralized setting require high levels of security, integrity, and controlled access, which are vulnerable to cyber attacks and data breaches. To address this, we propose a system that combines AES encryption, Shamir's secret sharing, blockchain, and IPFS. First, the image is encrypted so that it cannot be understood by anyone. Then it is divided into multiple shares using secret sharing. So no single part reveals any information. These shares are stored in decentralized system and access to control using blockchain. The image can only be reconstructed when a required number of valid shares are combined. In today's digital world, the sharing of sensitive images such as biometric data and confidential like army has increased rapidly. Most existing systems are using centralized storage, where all data is stored in a single server. This creates a single point of failure, meaning if the system is attacked or fails, all data can be compromised. To overcome these limitations, decentralized technologies like blockchain and IPFS has emerged, which distributed data across multiple nodes and improve security. In our work, we combine encryption, secret sharing, and decentralized storage to create a more secure and reliable image sharing system. Shamir has introduced secret sharing, which runs on threshold based security. And next, Diamond and Richmond developed AES encryption in 2001 for high level security. Satoshi Nakamoto in 2008 has introduced blockchain, which consists of decentralized peer to peer network. And finally, Bennett proposed IPFS, a distributed storage system that allows data to be stored across multiple nodes instead of single server. Existing image sharing systems face several major problems, mainly because they rely on centralized storage. This creates a lot of point of failure where if the system is attacked or crashes, the entire data will be lost. Although encryption is used, it depends on heavily key management, which is often centralized and vulnerable to compromise. In addition, my systems lack proper access control mechanisms, making it easier for unauthorized users to access. Because of these limitations, current solutions are not sufficient for securely sharing sensitive images. We researched that most previous works focus on individual techniques like encryption or decentralized storage. While these methods are effective on their own, they are often not integrated properly, which leads to issues like weak access control, inefficient key management. To address this gap, our contribution, we propose a complete integrated framework that combines AES, Shamir secret sharing, and IPFS for decentralized storage, blockchain for secure and tamper-proof access control. Traditional systems depend on one server, which can fail or be attacked. Sensitive images need stronger protection from hackers and misuse. Centralized storage is vulnerable to cyber attacks and data breaches. Here we use mainly the Shamir secret sharing. It is a method. A image is shared into multiple images, and it cannot, and each image cannot reveal any information. Instead of storing the whole data in one place, we split into n shares. A minimum number of shares called the threshold is required to reconstruct the original image. For example, if we create 5 shares and we set 3 shares, for any 3 shares, the original image can be reconstructed. And here we use Lagrange's interpolation. It is a mathematical polynomial function which is used to reconstruct the image. And here comes the methodology. First, encryption. The authorized user uploads the confidential image along with the threshold value and AES key. The image is encrypted using AES, so it becomes unreadable. And step 2, secret sharing. Next, the encrypted image is divided into multiple shares using Shamir secret sharing algorithm. This ensures that the data is not stored as a whole. Decentralized storage. These shares are stored in IPFS, which is decentralized system. The data is distributed across multiple nodes instead of a single server. Access control. When a user requests access, blockchain technology is used to verify and authenticate the user. Only authorized users can retrieve the required shares. Step 5, reconstruction. Finally, the required number of shares are collected and combined using Lagrange's interpolation. The reconstructed image is then decrypted using AES to get the original image. And how the model works. Here, first the secure access request. First, the user sends a request to the image. Then the request go to the blockchain, and blockchain verifies the user and gives the single share and the threshold share collection. Once verified, the system collects the required number of shares, that is K shares from IPFS. These shares are distributed across the network. Integrity verification. Before reconstruction, each share is checking using cryptographic validation to ensure it is not tampered. image reconstruction. Then the value shares are combined using Lagrange's interpolation to reconstruct the encrypted image securely. Final decryption. The reconstructed encrypted image is decrypted using AES to obtain the original image. Here, the entire process ensures confidentiality, integrity, and controlled access to prevent unauthorized reconstruction of sensitive data. And here is the first image shows the original image, and B image shows the AES encrypted image. C, D, E are the secret Shamir sharing, the N shares. The CDE cannot reveal any information. So we require threshold to any two images or of CDE reveal the original image F. And here is the comparison with centralized systems. Data storage here stored in a single server, and it is served in many servers. Security level, it is a single layer only encryption, but it is having AES, secret sharing, and blockchain and IPFS. Data exposure risk might be centralized, maybe data breach or attack. Uh, Unless the proposed method have the key is leaked, but the blockchain verifies the user is authorized or not. Access control. Here, anyone can access, like the authorized person can access. He can see all the data of the person. Here, blockchain uses strong blockchain authentication. Reconstruction, we can access directly in centralized system. It requires threshold shares. Resistance to attacks is moderate, and proposed method is high. Conclusion. The proposed system presents that for image sharing by combining AES, encryption, Shami secret sharing, blockchain, and IPFS, our system removes the limitations of centralized storage, such as single point of failure and risk of data breaches. Blockchain provides secure and tamper-proof access control, which IPS ensures distributed storage. The result shows that our system achieves secure, accurate, and lossless image reconstruction. Overall, our approach provides a reliable and scalable solution for secure image sharing. And here we increase that handle large images and reduce storage costs, support more use and faster transaction, foster image sharing and retrieval, make the system suitable for real-time applications. And here are references we use from Shamir and blockchain Nakamoto, and Bennett has introduced IPFS, and Damon Richman AES encryption. Okay, ma'am.
Okay, thank you so much, Krishna. Sir, do you have any questions for him?
Yeah. Krishna, I don't find any recent publication you are referenced. Any reason?
It is a we use it in it is collective projects. We are doing that in final as a final year project, and it is we use it as blockchain is a MetaMask, so that it is a local system. So
Okay. Why did you choose this threshold-based encryption scheme?
uh, for sometimes WhatsApp says it is end-to-end encryption, but we can't know that it is truly encrypted or not. For example, like confidential information like army or hospital records or any some personal images, if you share it any WhatsApp, we cannot have proof that it is end-to-end encrypted. So for this there is a threshold based encryption, that each any single image cannot reveal any information.
Okay. And how you're ensuring this data availability and persistence in IPFS?
Here IPFS is a decentralized storage, sir. uh, It stores the data across multiple computers instead of a single server. It can access through a local URL like HTTP, and it has a unique cryptographic hash.
So you're doing blockchain transactions, right? So
As
how, so what is that latency which you have introduced due to this blockchain transactions?
uh, in this blockchain, if a user try to access that image, so it checks the user is authenticated or not. It checks by the address of the person.
You mentioned
Like
about data set, right? Which data set you have used?
it is not data sets. It is a secret sharing algorithm.
So you're ensuring any metrics, I mean, evaluation purpose, any metrics?
It is By using the pixels of the image, it will constructing some end shares. Like each pixel is sharing into, for example, a original image having, and each pixel is sharing into like 5 shares. Each pixel is turned into blurred image.
Okay, that's it from my side. Thank you, Krishna.
Thank you, sir.
Okay, thank you so much, Krishna, for presenting. For the next presentation, we have Mark Thai Lok. Are you there in the meeting?
Okay, hello, I'm here.
Hello, yes. So you can start presenting.
Yes,
So he's
please
here to
wait.
present his paper titled as A Study on Deep Learning for Welding's Surface Inspection. Yes, I'll stop sharing. Yeah. Yes, it is visible. You can start.
Okay, I will start now. Okay, good afternoon, everyone. My name is Mike Thái Lộc from Cần University. Today, I would like to present our study entitled Our Study on Deep Learning for Welding Surface Inspection. This work focuses on developing an automatic system for detecting weld defects using 3D laser vision and deep learning techniques. The goal is to improve accuracy and enable near real-time inspection in industrial environments. This presentation is organized into 6 parts. I will start with the problem and the motivation of the present study, followed by the details about the proposed system and its architecture. Then I will present the dataset, the training setup, the model, and the experimental results. Finally, I will conclude our presentation with some key points. Now, let's take a look at problem and motivation. For a long time, well quality inspection is essential for structural safety in many industrial applications. Existing methods are often sensitive to noise, are not suitable for real-time inspection. In addition, industrial environments introduce challenges such as lighting variations and complex weld geometries, which make defect detection more difficult. Therefore, developing an accurate and efficient real-time inspection system remains a challenging task. To address this issue, we propose the following system. Our system combines 3D laser vision and deep learning for automatic weld surface inspection. First, a 3D laser vision setup is used to capture weld profile images, which provide detailed geometric information of the weld surface. Then, a YOLO VAN deep learning model is applied to automatically detect and classify different types of weld defects. The system is designed to operate automatically and efficiently with minimal human intervention. It is suitable for near real-time industrial inspection. Now, let's take a look at the system architecture. The proposed system has 4 main parts: an industrial camera, a laser projector, a conveyor mechanism, and a sensor unit. The laser projector creates a stripe on the weld surface, and the industrial camera captures the profile images. The conveyor moves the workpiece through the inspection area. A sensor detects the workpiece and triggers the camera to capture and save the image. After that, YOLO VAN is used for defect detection. Now, let us move on the dataset and training setup. In this study, we use a dataset of 140 weld profile images. All images were labeled by hand with bounding boxes in YOLO format. The defects were divided into 3 main categories. The first one, misalignment. The second one, concavity. And the last one, discontinuity. And we used 80% of the images for training and 80% for testing. For the model training, we used 150 epochs, a batch size of 16, and a learning rate of 0.0015. Next, I will show the training performance for all of you. First, let's take a look at the training performance of the model. As we can see from the loss curves, the training loss go down steadily during training. At the same time, the validation loss stay quite stable. This means the model learns well without clear overfitting. Next, the model achieved more than 80% at MAP at 0.5. In addition, the MAP at 0.5 to 0.95 is about 0.60 to 0.65. This shows that the model also has reasonable localization performance. Overall, these results show that the model performs well during training. Now, this slide shows the detection results of the proposed system. The image at the top is the original well profile image. The image at the bottom is detection result from the YOLO VAN system. As shown here, the model can detect and classify well defects accurately. It uses bounding box and labels to show each defect clearly, which help the inspector to see the defect well. In this way, the system can identify both the location and the type of each defect. Overall, these results show that the report system works effectively for well defect detection. Now, this is the quantitative results. The system was evaluated on 5 well samples labeled from A, B, C, D, and E. The average detection accuracy ranges from 89.0% to 94.79%, depending on the defect type and how serious it is. In general, the model performs better on clear defect patterns, especially discontinuity defects, while very slight misalignment is more difficult to detect. For composite defect cases, the model still achieves around 93 to 95% accuracy, which shows that the model works well on different cases. In addition, the inference time is less than 100 milliseconds per image, making the system suitable for near real-time inspection. The 3D reconstruction shown below also helps visualize the well surface geometry and defect distribution more clearly, which makes the system promising. In conclusion, this study presented an automatic well surface inspection system based on YOLO VAN model and 3D laser vision. The proposed system can detect well surface defects directly from raw profile images with good accuracy and stable performance. Experimental results show that the model performs reliably under different defect conditions and support near real-time inspection. However, slight misalignment remains more difficult to detect, which will be the focus of future work if possible. Therefore, the proposed approach has a strong potential for practical implication in industrial manufacturing environments. Thank you for your attention, and I would be happy to answer any questions.
Okay, thank you so much, Mark. Sir, you can go ahead with your question.
Yeah, Mark. What type of welding defects you are targeting?
Oh, sorry, I cannot hear you clearly. Can you repeat the question?
What type of welding defect you are targeting?
You mean what are of defect type I am working, right?
Yeah.
I'm working on three type defect. The first one is discontinuity. The second one is misalignment, and the third one, the last one is concavity.
These are the classes, right, which you have mentioned.
Yeah.
So how you handle the class imbalance in defect versus non-defect samples?
Uh, you mean how can I
Yep.
manage the non-defect sample, right?
Imbalance, yes, class imbalance. You said you are using testing and training data, right? So you will have three classes, as you mentioned. Okay, moving ahead regarding data set.
Let me think a second.
Yep.
Okay. When choosing a sample, we will focus on the three main kinds of defects as I show you, concavity, misalignment, and discontinuity, and the other more complicated defects will not be suitable for the system. Right now, non-defect symbols are handled as background in the YOLO VAN object detection framework. During training, images without bounding box are treated as normal symbols, helping the model learn to distinguish defect regions from non-defective areas and reduce false positives.
Okay, you mentioned about no overfitting in one of the slide, right? So how you are avoiding this overfitting in your model?
Sorry, I cannot understand clearly your questions.
Okay, no issues. You mentioned overfitting in one of the slide. Is it right?
Overfitting.
You can go through the slides. Yep.
Okay.
No issues. Uh, Even one more slide you mentioned that suitable for real-time inspection. Your model.
Is it possible for you to type the characters in the chat box?
Okay.
Okay, so sir, what you can do is you can write your questions in the chat box, and
Yes.
after few presentations, Mac, you can answer them.
No issues.
Yeah, so we will move on to the next presentation. So Tirupati Reddy, are you there?
Yes, ma'am.
Yes, so he is here to present his research work titled as An Efficient Hybrid LSTM GRU Stacking Model for Acoustic Vehicle Classification in Smart City Traffic Systems. So you can start presenting, Tirupati.
Good morning, sir. I am Tirupati Reddy and I am presenting our work on the smart traffic management in acoustic-based vehicle detection with ensemble more deep learning approaches. Our project focuses on detecting Mainly, our project focuses on detecting and classifying vehicle sounds using acoustic signals. We are using the stacking-based ensemble models, combining MLP and the multi-layer perception and DNN and LSTM and GRU. By extracting features like frequency and loudiness and amplitude, we trained the system on over 1800 audio files with siren sounds and root noise sounds and normal sounds. The model achieved up to 99.89% accuracy, making it highly effective on real-time emergency vehicle detection. Moving to an introduction. In smart city traffic congestion and delayed emergency responses are major challenges. Traditional camera-based systems fail in poor visibility conditions. So in our system, we are approaching the acoustic-based signal detection. So we are more reliable in noisy and low visibility environments to detect emergency vehicles and improve response time. So in this project, we are using the different deep learning approaches like GRU, ensemble GRU and LSTM. Next, move on to the literature survey. In this, in the previous published papers, some of the limitations are there that can overcome using these. Exercises mainly use techniques like MFCC and HM and basic neural networks. For those networks, they are failed some high frequency noises consumption. So for this, we are implemented the stacked LSTM models. In the exercise mainly face several issues like the current approaches using the LSCS and MFCC and PVM models. In that they have some limitations like moderate accuracy and poor performance in the real-time traffic noise, unlimited feature attraction, and inefficient handling for complex sound patterns. Also, there in execution, some of the single factors and single model techniques are used. So, in the proposed system, we are using the ensemble models. Our proposed system used a stacking ensemble deep learning approaches by using the MLP and DNN and LSTM and GRU. Mainly in these algorithms, LSTM and GRU are the modern algorithms like a long short-term memory. In these LSTM, we are using for recognizing the high frequency noises from the places, and GR gated recurrent unit is used for the up and down signal, up and down frequency sounds to recognize the vehicle sounds. Mainly in this proposed system, we are classifies the road noise and emergency sirens by analyzing acoustic visitors. In this project, we are using the dataset called siren features, where they are 1800 number of files, which contains siren sounds or noises. It will calculate from the Kaggle dataset. We also developed a Flask-based interface for real-time audio classification. In this project, we implemented due to high accuracy due to ensemble learning, better performance in noisy environments, and also ability to capture complex acoustic patterns and real-time data detection capability. The extension algorithm are used to improve the model by integrating GRU with LSTM. GRU simplifies the architecture and increase speed while maintaining accuracy. So this combination improves performance and makes the system efficient for large data sets. We are also recognize the real-time audio quality correctness. Then after the MP3 file converted into the dot wave file, because of the deep learning models did not understand the raw audio files, so we can convert into wave file. Then after it will give to the system, then that will recognize the siren sound or noise sound. Mainly in the system architecture, we firstly collect the data set from the Google dataset. Then after we can visualize the dataset to extract the features and shuffling the train models. In these datasets, we can use 80% of the train data and 20% of the test data. Mainly in these models, we are implementing these models for extracting the features like MFCC and male frequency septal coefficients, and also audio frequency for efficiently acquiring the properties. And also here measure eye performance, we measure the accuracy and precision and the recall and the F1 score. Then finally it will classify based on the parameters, audio parameters, it will classify the audio sound, which will noise sound or the silent sound. Then like that we are implementing. Mainly in this project, our main objectives are design a sound-based vehicle detection system to classify noise sound or siren sound based on the given input sound. And also we are implementing the deep learning models. See our outputs, the data sets we are using and proposed models and existing models. How to take the input from the user audio file. Then after it will classify the what the percentage of the respondent sounds. Then in the conclusion, our system provides an efficient solution for the smart traffic management using acoustic signals. The model achieves up to 99.89% accuracy, outperforming traditional methods. It enhances emergency response time and can be scaled for real-time smart city applications. Okay, thank you.
You're using LSTM and GRU, right? Or is it
Yes.
is it a parallel fusion?
Sir?
Is it LSTM to GRU or any parallel fusion you are using?
LSTM plus GRU.
Okay. So how your model mitigate this vanishing gradient problems rather than standalone RNNs?
Sir, please repeat the question.
You're considering any attention mechanism?
Yes, sir.
So how you are handling this vanishing gradient problem?
Sir, because of in deep learning approaches, raw data contains some noises and also some of the features like road noise and extra noises contains. For this, we are extracting the noise from the train the models, then extract the features like audio frequency and some graded models like MFCC and MLP like that. Then after we can give the model, give the trained audio file to the system. Then after we will recognize the models.
Okay. So for training and testing split,
Yes, sir.
you're using is it a fixed or it's a cross validation?
Yes, sir. It's a cross validation. Based on the data set we are taking, then based on that we are train the models on this.
So can your model operate in real-time traffic environments?
Yes, sir. By using some advanced machines like first we are classify the road noises with like taking the up to 5 to 10 seconds of the raw data from the real-time locations. Then after it will classify to the raw data to the wave file. Then it will convert to the it will classify the road noise or traffic signal. Then that model will be taken to the some of the advanced technologies. Then it will give the signal to the particular locations to move the vehicle to move the emergency vehicle.
Okay. Thank you.
Okay, thank you so much, Tirupati, for presenting. So, our next presenter is Dudi Gnana Prasuna. Is she ready with the presentation?
Yeah.
So, she's here to present her paper titled as Bone Fracture Detection in X-ray, a comparative evaluation of YOLO 8 variants.
Yeah.
So, you can start presenting.
Thank you.
Yes, and try to complete it within 8 to 9 minutes, okay?
Yes.
Yes.
So, good afternoon, respected judges and all the participants here. I am Gnana Prasuna. Today I am going to present our work on bone fracture detection in X-ray images, a comparative evaluation of YOLO V8 variants. So as part of the overview, today I'm going to cover abstract introduction, problem statement, literature summary, and followed by results, conclusion, and all the references. So basically, bone fracture detection in X-ray images is challenging due to noise and complexity. So in this work, we propose a deep learning based system using YOLO V8 models. So we, as we know, due to complexity and noise, it leads to prone to error detection. So we compare multiple variants such as N, S, M, L, and X of YOLO V8 models, as YOLO V8 is the most promising model of YOLO, which has recently shown highest accuracy. So manual diagnosis is time consuming and prone to errors. Therefore, deep learning can help automate medical image analysis. So problem statement is detecting bone fracture from X-ray images is difficult due to poor image quality, noise, and subtle fracture patterns. So existing machine learning models mainly focus on classification but fail to provide localization of fractures, especially when there are very small little fractures. So as part of the literature survey, we have gone through so many literature surveys where it has shown as CNN-based models basically provide good classification accuracy, but they lacked in localization. So YOLO-based models improve detection speed, but still face challenges in detecting small fractures. So recently, YOLO V8 models showing promising results, but comparison of variants is very limited, where we started our work to compare different versions of YOLO V8 and show the highest accuracy, which will be better model to perform. So main objective of our project is to develop an automated fracture detection system, which is not only for detecting, but also to localize the fractures using bounding boxes and to compare different variants of YOLO V8. And this is a proposed methodology where we started with the pre-processing. We have collected the dataset from the Kaggle, which is a real-time dataset of X-ray images containing all time valid and test datasets. And the proposed methodology of our project is starting with the pre-processing techniques, feature extraction, and labeling the images, bounding boxes with clear measurements using different tools, and then object detection, recognition, decision making, and output. So for the optimization, we have run the epochs for 50 first and then for 100 and compared all the versions with 100 epochs. So this is the system architecture which we basically collected from the all previous work. So these are the results showing, first graph is showing MAP square across 0.5 epochs and this is 0.95 epochs. So these results shows that smaller versions like small m are performing better compared to larger values due to overfitting. So smaller versions, and we also compared precision and recall also. Here also the result shows as smaller and medium models performed better than larger models. And as we see, YOLO V8 M and S show stable precision and recall, whereas S has the lowest inference time, making it suitable for real-time applications. And as I wanted to conclude that, so we developed a deep learning based model system using YOLO V8 variants. Among all models, YOLO V8 provides the balance between accuracy, speed, but the system successfully detects and localizes fractures. So this approach can assist doctors in faster and more reliable diagnosis. And these are some references that we followed as the base papers. So thank you for your time and attention, and I am happy to answer any questions.
You used Kaggle data, right?
Yes, sir.
Okay. How many images and fracture classes were included in that?
Uh, there were almost 7 to 8 fracture classes, sir. And training dataset was about 3,600 images, where we faced some issue to run more epoxes using, as the GPU doesn't support for the images, so we limited it for 50 to 100 epoxes and we collected the results.
Okay. For training model, which strategy you used?
So we used the inbuilt YOLO V8 technique only, sir.
So is it supervised or unsupervised?
It is supervised.
Sure.
Yes.
Okay. So your system is highlighting fracture region, I mean heat maps or some kind of a thing, GradCam.
Yes, sir, it is highlighting. If you wanted to show the results, I can show the results, like the images.
No issue, no issue. Okay. Thank you.
Thank you.
Okay, so next we have Lakshmi Priya Vijayan. Is she present in the meeting? Mm, I think she's not there. Any of her co-authors is present? Okay, no. So let's move forward. And we have Windy Permata Suyono. Is she present?
Yes, I'm present, Miss.
Yes, so she's here to present her work titled as Development and Validation of an AI-driven Digital Audit Maturity Index, the moderating role of internal control maturity in advancing SDG 9. So you can start presenting.
Yes, Miss.
Yeah.
Okay,
Yes.
good afternoon, distinguished professor, respected reviewers, and fellow researcher. My name is Windy Permatasiono, and it's great honor for me to present my research entitled Development and Validation of an AI-driven Digital Audit Maturity Index, or DAMI, the moderating role of internal control maturity in advancing SDGs 9. This study is driven by the rapid digital transformation of auditing, especially in SMEs that face resource limitation but must adopt to technology. And the digital transformation is significantly reshaping auditing practice through automation, advanced analytic, and intelligent system. This technology improve audit efficiency, accuracy, and coverage compare to traditional manual procedure. And then for SMS, adopting digital audit tools is no longer optional, but a strategic necessity to improve transparency, accountability, and long-term sustainability. At the same time, the advancements of AI enables continuous auditing, anomaly detection, and then predictive risk assessment. However, successful implementation of AI depends on organizational readiness, including data quality, digital skills, and technological infrastructure. And in the context digital audit maturity reflect how well digital technologies are integrated into audit process. However, most existing studies focus on large organizations, leaving a significant gap in SME research, especially in emerging economies. And then additionally, internal control maturity plays a critical role in ensuring that digital and AI-based audits are reliable, ethical, and transparent. Despite this, empirical evidence on its moderating role remains limited. The study addressed two main research gaps, and the first, the moderating role of internal control maturity and the lack of validate measurement tools for SME. Therefore, this study aims to develop and validate an AI-based digital audit maturity index or dummy, and then examine the relationship using PLSM and the last support sustainable atau SDGs 9, Sustainable Development Goal 9. And then research method, this study adopt a quantitative research design using SAM atau structural equation modeling with PLS. The objective is to examine the influence of digital audit technology and AI readiness on digital audit maturity with internal control maturity is a moderating variable. The sample consists of 120 MSME owners, managers, and accounting staff in Indonesia, selected using purposive sampling. Data were collected through a structured online questionnaire. The instruments were adapted from validated scale and adjusted to the SMA context. For analysis, we use part PLS evaluating both measurement and structural model. Reliability and validity were assessed using congruence alpha, composite reliability, AV, and discriminant validity. And then, before testing the hypothesis, we first validate the measurement model. On the left, you can see the convergent validity result. All factor loadings are above 0.7, which confirm that the indicator strongly represent their respective construct. On the right, you can see the discriminant validity table, so that the STMT value are all below 0.9. This means that each construct, digital audit technology, AI readiness for audit, internal control maturity, and digital audit maturity is distinct and not overlapping. Together, this result confirm that our measurement model is both reliable and valid, providing a solid foundation for the hypothesis testing. And then here we present the construct reliability and validity. You can see in table 2, all congruence alpha value are above 0.7 and composite reliability value exceed 0.87, and the AV value are also above 0.5. This confirms that all construct digital audit technology, AI readiness for audit, internal control maturity, and digital audit maturity are reliable and valid. And in the table 3, the R-square value for digital audit maturity is 0.627, which means that about 62.7% of the variance in audit effectiveness is explained by independent variable. Based on change criteria that is considered a moderate level, indicating that our model has good explanatory power. And the next, direct effect testing result. Bootstrapping with 5,000 resample was used to evaluate path coefficient, SA, p-value, and t-value, and confidence interval. A hypothesis is accepted if data statistic more than 0.9 and p-value less than 0.05. And then our results show the 3 strong direct effect, and the first, digital audit technology has significant positive effect on digital audit maturity, and the second, AI readiness also has significant positive effect, and the last, internal control maturity show a strong and significant direct influence. This result indicate that both technological capability and organizational governance play critical roles in enhancing digital audit maturity. In other words, CMS that invest in digital tools and prepare for AI adoption tend to achieve higher levels of audit maturity. And the next, indirect effect testing result. We test internal control maturity as a moderating variable. The hypothesis is accepted if test statistic more than 1.9842 and p-value less than 0.05. We found an important result. The effect of digital audit technology on internal control maturity is positive and statistically significant on digital audit maturity. Internal control maturity does not significantly moderate the relationship between AI readiness for audit and digital audit maturity. This finding indicate with well-developed internal control system, AI readiness does not automatically enhance digital audit maturity. This suggests that in SMS, AI readiness may still be conceptual and not fully integrated into operational audit practice, such as analytical or continuous auditing. And then discussion and conclusion. Overall, this finding highlights several important points. First, digital audit technology and AI readiness significantly improve digital audit maturity. And the second, internal control maturity plays a strong role, but as a direct enabler rather than a moderating factor. From a theoretical perspective, the TAO framework is partially supported as a technological and organizational factor influence outcome independently rather than interactively. From this resource-based view, IR readiness can be considered an intangible resource, and however, it only creates value when supported by complementary capabilities such as skill, human resource, integrated system, and effective process. In conclusion, internal control maturity acts as a direct enabler, not a moderator, and then she must focus on practical integration of AI in audit process, not just readiness. And then SMS should move beyond conceptual AI readiness and focus on the practical integration of AI into audit effective. And then limitation. The study has several limitations, and the first, the use of cross-sectional and self-reported data may introduce the bias, and then potential bias in existing digital audit adoption and internal control maturity, and then context, and the second, focus and SMA in single country limits generalizability, and the third, the model does not include external factors such as regulation, culture, and ethics. Future research encourages to integrated external focus and incorporate broader contextual factor, and then use longitudinal or mixed method approach, explore the dynamic evolution of AI auditing and integration and its integration with internal control system. This improvement will strengthen the dummy framework and provide more comprehensive insight. And in summary, the study contributes by developing and validating the dummy framework and providing empirical evidence of AI driving audit or transformation in SMA. It also offers practical insight for policymakers and practitioners in supporting digital transformation aligned with SDGs 9. Thank you very much for your attention.
Oh, can you define digital audit maturity you mentioned?
Can you repeat again, Mister?
How you will define digital audit maturity?
Or can you please type the question? I apologize for the inconvenience.
What you
Audit.
can do is you can put your answer in the chat box itself so I can continue with the other
Okay.
presentations.
Okay, I'm so sorry because
No, that's fine.
okay, digital audit maturity maybe refers to the extent to which digital technology and effectively integrated to the audit process. It reflect how well an organization utilize tools, maybe such as a data analytic, automation, and AI across all audit stage, planning, testing, and reporting to improve efficiency, accuracy, and insight generation. Thank you, Mister.
Okay, thank
And
you.
then, how internal control maturity? Okay.
Okay, so let's move forward to the next presentation. We have with us Mr. Sachin Ratnaparkhi to present his research work titled as Explainable Artificial Intelligence for Trustworthy Internet of Things Systems, Models, Methods, and Challenges. Sir, are you ready?
Yes, I'm ready.
Okay, so you can
Am
start.
I audible?
Yes, sir, you're audible.
Thank you.
Yeah. So you can present your screen.
Yeah, I'm not able to share it.
Yeah.
Yeah, you guys can see my screen, right?
Yes, the screen is visible. You can start.
Um,
The research paper is being
yeah,
presented.
sorry.
Yeah.
The other window I opened because of some, yeah. So, good afternoon, everybody, and Honorable Judge. My name is Sachin Ratnaparki, and I'm going to explain my studies based on the explainable artificial intelligence for trustworthy IoT things, system, model, methods, and challenges. Under the guidance of Dr. Professor Parikshit Mahale and Pankaj Chandra, I done this study and literature review. So overall, the outline is based on the background, trustworthiness of IoT things, need of explainable AI in the IoT things, and proposed architecture, methods, and definitely research challenges and future work. So I will start with the introduction. As we know, there is a rapid growth of IoT system across all the domains. Like we are using in different day-to-day life activities for a smart car, smart home appliances, smart thermostat, or smart security cameras, and etc. So this integration of AI, basically for AI automation and decision making. For example, when you are mowing on the lawn, giving lawn shower on your backyard or your garden level, whenever you give any automating based to the rain harvesting system or anything, it always work on the automation based on the weather sensing and all, and it make a decision, and it's giving watering or not. It based on that it will take kind of thing. This is a small example we can use for using the day-to-day challenges. Definitely, the black box nature of the AI model, this there is a definitely lack of transparency always, and key issues like trust, accountability, and always the requirements of the regulatory compliance for documentation and to safety requirements. So these all to be getting covered in all systems along with the XAI, I would say XAI. So, as we know, the overall IoT architecture is based on the different layered IoT architecture, like perception layer, sensor devices are there, actuators are there to get some input data. Then network layers are there where it make communication. Then processing layers based on the edge, fog, and cloud computing based on the different levels of processing data. Then application layer, and definitely once you have this requirement, you do this algorithm with all these different layers of the process, then there are the challenges of diversity, then resource constraint and real-time processing. So that is definitely sometimes happen, we cannot able to achieve current architecture, but once you have along with the explainable AI, then it will be definitely more repeatability and robustness and reliability will be there. So currently, if you see in the trustworthiness in IoT system, like key dimensions are transparency, reliability, and the robustness in the sense of how the it consistent and the explanation remains when small input given to the any system, and it gives you the outputs based on that algorithm. Then the privacy, accountability, and the traditional system focus only on the data security and communication integrity. But if we add that based on the decision with the AI, explain AI, then it will be definitely a complete foolproof system which we can be able to run definitely based on there are future scopes and challenges as well. I will try to explain in the next few slides. So, explainable AI's fundamentals are basically on the make AI decision interpretable, And the types of interesting models are design trees, linear models, the post hoc models like LAM and SHAP to interpret the complex black box machine learning models, categories just like local versus global, which is specific prediction versus decision based on the entire data set, and model and specific model and logistic as well. So why this XAI, the explainable AI, is critical for IoT? The definitely first thing, the safety critical appliances like for healthcare, smart cities, and any smart devices which we use with the based on the AI help. Then it which enables decision validation. Always it will take whole circle of validation, and then it will give the proper output with error analysis or and based on the regulatory compliance also. Because a lot of countries now have for example, US AI compliance policies are there. So different countries have different nominal protocols and which we want to follow with generating any AI database or any architecture. And definitely it improves user trust. Then human collaboration will be there in that case, and IoT devices are disturbed and dynamic in nature, so that will help us to have the complete set of requirements if we add this into the day-to-day IoT devices. So a taxonomy of overall XI models are interesting explainable models, which is decision trees, rule-based system, post-HOC model, LimeSharp, which I already mentioned earlier, and the deep learning explainative is GrandCam and attention mechanism. Definitely deployment, however, XAI, device level, edge level, or cloud level, we can add, and based on that, we can generate the whole database. The proposed architecture for that is a multi-layer explainable IoT framework, which is edge, which is local explainable, then content aware refinement for fog, and cloud-based is the global where we can add all the database and try to generate that data. And the features in the trust evaluation, feedback loop, and the human in the loop. Definitely, overall, with the help of this is the explainability by design, so that we can have robust module which will give the outputs very pretty quick and with proper validation. This is a one schematic diagram for proposed architecture where the physical lot AI environment is there. So sensors and actuator will get some initial layer. Then we will have the engage intelligence layer, which data processing and noise filtration. Then lightweight AI interface where edge models will be happen, and one device with explanation will approximate. Then fog and gateway layer where we can have the trust monitor and edge fog explanation refinement. And in between, always there will be the governance and layer where explanation, audit, and compliance store will be there. For each and every step, we can try to get in center for that, because compliance is always be important. And the human application and layer where user and operator interface with role awareness explanation, human in loop feedback model we can always add. And for cloud intelligence layer, we will deep learning models and global training, post HOC, which XI engine and SHAP, all these requirements we can add based on explanation, contingency signal, and then security and privacy are the key members. So based on this typically architecture, we can try to add this XCI into IoT architecture. Comparative analysis of dimensions like application domain, AI model type like generative AI, or explanatory technique, deployment layers, and it will try to get comparative analysis with the different observation, like focus on transparency only, limited at real-time evaluation, and pretty much lack of edge-based solution. Definitely, this is a concept or study where we can find these research gaps and challenges, which lack of undefined frameworks, like structured approach that integrates multiple components, high computational cost like GPU, CPU, and data centers, etc. So limited evaluation metrics, like lack of standardization, relies on the subjective human evaluation and absence of ground truth. And privacy, which is very sensitive for private and proprietary data always, which can happen in the different applications, and where poor human-centric evaluation also with to be added. So definitely these are the uh, pretty much gaps we can add, and for further future direction and conclusion, where executive by design models development aware XAI standard benchmark and human-centric explanation. So, and conclusion, XAI is essential for all trustworthy IoT devices because, as I mentioned, for reliability, security, compliance regulation, we need all the data to be get properly and validation happen each and every phase, and so that the error-free and debug runs or outputs can be get always, and need integration across the all layers, enable transparent, reliable, and secure system which can be handed over with this integration with the IoT system, and based on that we can have different uh, proper data at the end of scenario. These are the few references which we use to write this study paper. Yeah, and this concludes my presentation. Any questions and answer?
Yes, which layer this XAI is implemented?
This is in, as I mentioned, in Lime and SHAP.
These are the techniques which you have implemented, right?
Yeah, so the local plantation, the frameworks like surrogate models or feature attribution kind of thing.
Okay, I mean, you implemented this or considered this as a edge or fog or cloud layer.
Right.
So all or any specific layer you
Definitely the cloud is the better for the global expansion and validation, I would say.
So how you measure the trust in your system?
Yeah, that is basically based on the different validation and how the properly the compliances or regulatory requirements which can be monitored every other time, and based on that we can get the more trustworthiness for end users.
Okay. So you've used sensor data, right, as IoT data?
Correct. Or actuators.
Okay, so how you are handling the noise or incomplete or maybe streaming data?
For noise, basically, we can add some different levels of initial layers, right? Where we can try to filter it out based on the data pre-processing or any lightweight AI interface, where we can get these edge models, and based on that we can try to get noise filtration.
Oh, thank you.
Okay, thank you so much, Sachin sir, for presenting.
Thank you.
So let's move to our next paper. So next presenter is Deepika R. She is here to present her paper titled as Network-Based Multi-Omics Drug Repurposing in Hu- Huntington's Disease. So Deepika, are you ready?
Yes, ma'am. I'm
Yes,
ready.
so you can start presenting. Yeah.
Good morning, everyone. I'm presenting my work titled Network-Based Multi-Omics Drug Repurposing for Huntington's Disease. These are the project contents, starting from the clinical problem, research aim, objective and goals, and to the methodology and lastly about the result and discussion.
Deepika, your voice is a little low. Can you please increase the voice also? The clarity is a bit missing. So,
Okay, ma'am.
little bit.
Is it okay now?
Yes, you can start.
Ah, the clinical problem, Huntington's disease. Huntington's disease is a progressive neurodegenerative disorder characterized by motor dysfunction, cognitive decline, and psychotic symptoms. It is 100% genetic, that is caused by CAG repeat expansion in the HTT gene, and it currently has no cure. Existing treatments are only symptomatic. The major challenge is the lack of effective disease-modifying therapies, which highlights the need for faster and more efficient drug discovery approaches. The research aims to develop an AI-driven network-based pipeline that integrates the multi-omics data and clinical data. The approach helps model disease-specific molecular networks and identify repurposable therapeutic candidates for Huntington's disease. It identifies HT-specific molecular dysregulation and prioritizes the repurposing therapeutic candidates. Objectives and goals. Objective 1 are first to integrate multi-omics and clinical datasets to distinguish HT from control groups. Second, to identify key dysregulated genes and pathways using network-based analysis. And third, to prioritize potential drugs using repurposing probability and signature reversal scoring. Methodology overview. Our methodology consists of a six-step pipeline starting from data collection and pre-processing, followed by disease signature identification, network construction, drug integration, and drug disease mapping, and finally, candidate ranking. In methodology, step 1 will be data collection and pre-processing. In the first step, we collected drug data from PubChem and multi-omics HT data from Kaggle. We prepared pre-processing, including binary classification of HT versus control groups, and covariate correction to remove biases like age and sex. Step 2. This is signature identification. In this step, we perform differential expression analysis and constructed co-expression networks for both HT and control groups. We then identified differential network changes and extracted the most dysregulated genes associated with the disease. Step 3 will be feature construction and network engineering. Here, we perform pathway enrichment analysis on the dysregulated genes. This allowed us to identify key biological processes and neurodegenerative pathways involved in Huntington's disease and constructed a disease-specific network. And step 4, the drug dataset integration. We then integrated drug data by parsing PubChem identifiers and mapping drugs to their target genes. We filtered relevant and FDA-approved compounds to ensure clinical relevance. Step 5. Network-based drug disease mapping. In this step, we developed drug-gene interaction networks and evaluated their overlap with dysregulated HT genes. We computed repurposing probability and signature reversal scores to assess its therapeutic potential. And the last step, drug ranking. Finally, we ranked and candidate drugs based on a combination of repurposing probability, signature reversal, and also their biological relevance. This resulted in a prioritized list of potential therapeutic compounds. These are the results. And at first, it will be top 10 drug repurposing candidates for Huntsy. These are the top 10 taken among the 100 candidates we have gained. And these candidates in our analysis identified 10 top drug candidates showing high repurposing probability above 0.97 and strong negative signature reversal scores. These results indicate a strong potential for reversing disease-associated molecular signatures. The key findings: the combination of high repurposing probability and strong reversal scores suggests that these drugs can counteract disease-specific molecular dysregulation rather than targeting isolated pathways. The biological interpretation: among the several top candidates have strong biological relevance. For example, metprestninone shows anti-inflammatory effects, whereas Susawork target DNA damage pathways and timolol may stabilize neuronal signaling. This supports the validity of our computational predictions. PCA analysis: the PCA result shows that the first two principal compounds explain only 34% of the variance. This indicates that Huntington's disease is a highly complex and influenced by multiple subtle molecular factors. Heat map analysis: the heat map shows weak inter-feature correlation, suggesting that biomarkers act independently. This further supports the heterogeneous nature of the disease. Correlation network analysis: the network shows no single dominant gene driving the disease. Instead, multiple interacting pathways contribute to disease progression, reinforcing the need for network-based therapeutic strategies.
Deepika, sorry to interrupt, but your slide is still on the first slide. Like the screen is on the first slide. It is not changing. Yeah, yeah, now it is changed. Yeah, yeah,
Okay, sorry, ma'am.
yeah, that's fine. You can continue.
Yes,
Yeah.
next will be drug gene mechanism Sankey diagram. Here, the drug gene mechanism is presented using Sankey diagram. This visualization shows the relationships between prioritized drug candidates and their molecular targets, associated biological processes in Huntington's disease. Each drug is connected to more dysregulated genes or further linked to the relevant pathways. This helps us to understand not just which drugs are important, but also how they interact within the disease network. Importantly, we observe that multiple drugs target overlapping pathways, reinforcing the idea that Huntington's disease is a network driven disorder requiring multi target therapeutic strategy. Gene expression level versus CAG repeats. We observe almost no correlation between HTT gene expression and CAG repeat length. This, this suggests that CAG expansion affects the protein toxicity rather than gene expression levels. Protein aggregation analysis. Protein aggregation level versus CAG repeats. Similarly, protein aggregation shows weak correlation with CAG repeat length. This indicates that aggregation is influenced by additional biological factors such as cellular stress and protein folding mechanisms. Future, future research and directions. It is in future incorporating an automated ADMT profiling model and prediction including the prediction of blood-brain barrier permeability, drug-drug interaction analysis, and also CNS multi-parameter optimization shows. This will improve clinical applicability and validation of the proposed drug candidates. In conclusion, we have successfully developed an AI-driven multi-omics pipeline for Huntington's disease. We identified key distributed networks and prioritized promising drug candidates. The framework is scalable, reproducible, and provides a strong foundation for future therapeutic development. The final takeaway is Huntington disease is a network driven which arises from multi-gene, multi-pathway dysregulation. Here, AI enables precision discovery through the use of multi-omics and network modeling. Here, the top candidates demonstrate high repurposing probability and strong resignature reversal. This pipeline is faster and scalable for the drug discovery. It also helps to reduce cost, clinically translatable, and also supports precision medicine. These are the key references supporting our methodology and findings, including recent studies on drug repurposing and neurodegenerative diseases. Thank you for your attention. I will be happy to take any questions.
Okay.
Sir, any questions from
Yeah,
your
yeah.
side here?
You mentioned about omics layers, right?
Yes, sir.
Which omics layers were included?
Transcriptomics, genomics, and also proteomics.
So how do these omics layers complement each other biologically?
The values. Like, 1 minute, sir. The omics data are each have specific values. The values will be maybe from a smile string or can be the values are from the binary data sets. Also, these binary data sets have specific qualities like if the protein can be aggregated or not for the specific smile strings. So these smile strings are taken for the drug composition and also the disease composition. So they are overlapped based on the smile strings and the values are taken based on that.
You're implementing this, integrating this multi-omics data
Yes, sir.
at which level?
Sir,
You are going for network, right? So any normalization techniques you're using to handle this heterogeneity?
can you come ahead?
How you are integrating this on
Integrity.
network? Yeah.
Here I have used here my biological network is built based on the network-based learning curve. Here the nodes are genes, proteins, and drugs, where the edges are the interactions. Here machine learning is used to identify important nodes and measure how strongly a drug influences the drug pathway. Here, random forest is used uh, to identify the gene expression similarities and the drug target interaction scores and network proximity. So,
Yeah. I want to know that how AI you're used here.
I have used AI to integrate all these values. So it's not easy to integrate these all these multi-value data sets since the data set is up to 48,000. So to integrate this, the AI is used to integrate the multi-omics data and learn patterns between the drugs, genes, and disease pathways. It is also used to predict which drugs are most likely to work for the Huntington's disease.
Oh, thank you. That's it from us.
Okay, thank you so much, Deepika, for your presentation. So next we have Nandita B to present her paper titled as Prediction of Attention Deficit Hyperactivity Disorder in Children Using Multimodal Approach. So Nandita, are you present in the meeting?
Hello, am I audible?
Yes, you're audible.
Yeah, we are there. We are like three people in the project. We all are present.
Okay, so you can start presenting, Nandita.
Sure.
Hello. Hello. Good morning, everyone. Am I audible?
Yes.
Yes.
Hello. Good morning, respected panel members. We are presenting our project prediction of attention deficit hyperactive disorder in children using a multimodal approach. And this project is carried out by our team under the guidance of Mrs. Vani K.S. from Information Science Department. Next page. And our presentation is structured as follows. And ADHD is a neurodevelopmental disorder characterized by the symptoms of ADHD are inattention, hyperactivity, and impulsiveness. And you may wonder why ADHD is important because early detection of ADHD helps improving learning ability, behavior, and overall development of the child. And it is more common in children because their brains are still developing, especially in areas controlling attention and behavior. And the factors like genetics, parental issue, and environmental issue contribute to occurrence of ADHD in younger children. And our problem statement for this project is development of a multimodal system to detect ADHD in children through eye, facial expression, and speech analysis, while raising awareness among parents and educators to enable early intervention. After listening to this problem statement, the question arises why multimodal? Because ADHD symptoms are complex and cannot be captured accurately using a single data source. So we are using multimodal here. And actually, we have referred to 27 such research papers. As of now, in this presentation, we have added 10 of the research papers. The firstly, we can see that comprehensive analysis of attention. This is the paper title, and it was published in 2025. We have arranged every paper in chronological order, and the observation which was done here were ML and DL techniques were showing promising result in ADHD. And the conclusion from this paper we got that a unified approach integrating optimized machine learning and deep learning models can significantly improve the accuracy. As such, we have referred to 10 research papers. Nadita, can you please go to research gap? And my teammate Nandita will continue from.
After looking at these 27 research papers, we did find some research gaps. The research gaps included there was no such strategy for finding the combined cognitive and physiological training. That is, most of the interventions either focused on the attention of the children with ADHD or either on solving the problem using some simple basic breathing and pulmonary exercises with very few integrating both of these together. The second one that we analyzed was that there was a lack of truly multimodal detection systems. That is, most of the studies rely on only a single modality, that is, they either focus on the eye gaze, the facial expression, or speech, rarely combining all of these together. The third one was moment by moment analysis. That is, ADHD is best assessed through detailed analysis. And the last one was accessible screening tools. The current methods largely depend on costly equipment such as EEG signals, the VR setups, and there is no such affordable, wearable, and real time solution as of now. Moving on, the objective that we try to accomplish by this project and we try to bring out was to implement a system that monitored several clinical features such as inattention, IQ, performance IQ linked to ADHD. The second one was to collect the voice recording that engages children in short convos, just to analyze the speech disfluencies, attention lapse, and the response patterns. Also, it was to raise the awareness and provide actionable insights for parents and teachers so that they could analyze any early symptoms in children having ADHD. Basically, the methodology that we used was first we did the data pre-processing. That was the raw data was cleaned and synchronized. We removed the noise and the null values. The next step was feature extraction. That is, we took the raw data and converted it into useful information that a ML model can understand and easily learn from. The third was feature fusion, wherein the extracted features are combined using early, late, or hybrid strategies. The fourth one was model training. That is, we trained two models, that is the DeepFoNet and the TabNet, using cross validation and class balancing to detect the ADHD symptoms. Next, we performed the model evaluation. That is, the performance was assessed based on the accuracy, precision, recall, along with the confusion matrices for a better analysis. Then we did the model optimization. That is, if at all we found that the results were unsatisfactory, hyperparameter tuning, feature selection, and retraining are applied. And then we got the output. That is, the final model provides a classification result indicating whether the ADHD symptoms are present in a particular child or not. This is the flowchart, the methodology flowchart according to the methodology steps I explained. My friend Nandita will be continuing about the full implementation and the dataset details.
Thank you, Rishika. Now let's talk about the complete implementation of the project. So starting with the dataset. The dataset was collected from Kaggle from the hospital data, so which consists of 29 attributes and 486 columns, where each will represent the individual case with clinical, behavioral, and demographic information. So the starting step which we did is a pre-processing steps. So firstly, we have loaded the data set and we have checked for if there is any inconsistencies, like there is any empty values or any irrelevant attributes. So the missing values were represented by NI or blank were replaced.
It keeps your body cool and your stomach happy. So this
The new the numeric columns were filled with the mean values and the categorical columns were replaced with the mode values, which is the most frequently occurring values, to prevent the data integrity. The categorical features such as gender were labeled encoded to convert them into numerical form, which is suitable for the model training. All the numerical features were standardized using the standard scaler to ensure the equal contribution of each feature. So as my friend already told, we have used two models for using the training. So the first is a DeepFoNet and the second is TabNet. So a DeepFoNet is based on the EEG classification, which is a deep layer network. So it is a custom-built deep learning model inspired by EEG classification networks, designed to learn high-level abstract patterns from the input features, which consist of fully connected layers with batch normalization, ReLU acting as the activation function, and the dropout function for better generalization. The second model used is TabNet. TabNet is basically used for column dataset. So our dataset consists of CSV values, so that's the reason why we use TabNet. So TabNet is a deep learning architecture specifically used for tabular dataset combining decision tree interpretability with neural network power. It uses sequential attention masks to focus on the most relevant features at each decision step, improving learning efficiency and explainability. Built with feature transformer and decision step layers that learn sparse feature representations dynamically. We have used two models, which represents a hybrid and ensemble model, which combines the prediction probabilities from both the models, leveraging deep net's deep feature extraction and tabnet's attention-based feature selections in order to improvise on the accuracy. So these ensemble enhances classification accuracy and robustness, balancing generalization and interpretability. So as a result of using both the models, we have achieved an accuracy of around 90.09%, outperforming individual models and demonstrating strong predictive capability. So now here are some snapshots of the implementation. So first we have the confusion matrix consists of the hybrid model. And then we have the epoch versus accuracy graph. So here we can see that as the epoch increases, the accuracy is also increasing, which shows that the training is going in a right direction. Now we have the epoch versus loss graph. So as the epoch is increasing, the loss is decreasing. We have also provided a classification report which consists of precision, recall, F1 score, and support. We have provided a collab link of the implementation done. For the reference, we have cited the research paper which we have used in order to make the implementation. Thank you all. Now we are open to questions.
In your references, you didn't mention the years. Apart from this, regarding data set, you use Kaggle data set, right?
Yes, we have used Kaggle dataset.
So what are the data modalities which we are used?
So the dataset consists of features like performance of an individual candidate. So basically, it was featured among children because the ADHD is more in children. So it consists of the site information, means from where the data has been taken, like age, gender, the ADHD score, index, performance, and IQ.
Any data regarding behavioral assessment?
Behavioral assessment.
Sir, actually we have used clinical and behavioral data with multiple attributes for better prediction, sir.
So all the data that the data set consists is actually taken from hospitals. That is, the children were monitored during some major activities, maybe like just speaking or something like that, to analyze all these features like verbal IQ and the speech disfluencies and all those.
Yeah, if we take one scenario, for example, some data is missing. So how you are handling this missing modalities? For example, if I say I consider behavioral and clinical records as the modalities, right? So out of these two data modalities, if some data is missing, how you are handling? Maybe in behavioral, the questionnaires or surveys which we have collected, some questions are not included so that we are missing that important data, because based on this you are going to implement, right, next steps processing. And you are saying multi-model. Hope you got my question. My question is simple. If for some children the data is not proper, how you are handling this missing thing? Is your yeah?
Can I answer?
Yes, sir.
For the data handling, we have performed certain steps. So starting with finding the mean values. So if it is a numerical value column, we will replace the value with the mean value of the column. If suppose that child's data is not there in the data set, and if it is a categorical value, we have to replace it with the mode values. And this mode technique was also used in order to deal with the class balance.
So you are saying ADHD data sets, right? And this class imbalance. So you are
Yes.
handling by using the mean values.
Yeah,
Because
mean
again,
values.
missing data handling is different and class imbalance is different.
Yes, yes.
You also mentioned the optimization techniques and hyperparameter tuning methods. Which methods you are used actually for optimization and hyperparameter tuning?
For hyperparameter tuning, firstly we checked with the epochs. So initially we had trained with 50 epochs. So that we have got a bit of less accuracy than how much we got now. So then we have changed the number of epochs to 100, so where we could achieve the accuracy of 90%.
So why you are not use single model modality model?
So
Why
because when
multi-model?
we used a single model, we couldn't achieve the same accuracy that we were achieving using two hybrid models. And also we got to know that we saw that the prediction was much accurate with a better accuracy. That's the reason we combined two hybrid that is, we combined two models and made a hybrid approach.
Okay. That's it from my side. Thank you.
Thank you, sir.
Okay, thank you. So next up we have Shailaja P to present her paper titled as a deep learning framework using CNN, LSTM and transfer learning for multi-class detection of COVID-19 and pneumonia from chest X-ray images. So Shailaja, are you ready?
Yes, ma'am.
Yes, so you have to wrap it up in 8 to 9 minutes quickly. You can start sharing.
Good morning, respected chair, distinguished participants, and fellow researchers. I am Shailaja P. And it's my privilege to present our research titled A Deep Learning Framework using CNN, LSTM, and Transfer Learning for Multi-Class Detection of COVID-19 and Pneumonia from Chest X-ray images. This work is carried out in collaboration with Dr. Jayasudha JS from the Department of Computer Science, Central University of Kerala. And the presentation is structured into the following segments: introduction, literature review, problem statement, objectives, methodology, analysis, conclusion, and some references. And COVID-19 and pneumonia continue to pose significant global health challenges, contributing to substantial mortality and healthcare burden. And accurate, timely diagnosis is critical for effective treatment and containment. However, traditional diagnostic approaches often involve high costs, longer processing times, and dependence on specialized infrastructure. In contrast, chest X-ray imaging offers a cost-effective, faster, and widely accessible alternative, making it highly suitable for large-scale screening. In this research, we explore the application of advanced deep learning techniques to classify chest X-ray images into three categories: COVID-19, pneumonia, and normal cases. These are the literature reviews. Existing studies demonstrate the growing role of deep learning in medical imaging. Techniques such as convolutional neural networks have shown promising results in disease detection. However, most prior works focus mainly on binary classifications, limiting their applicability in real-world clinical settings where multi-class classification differentiation is required. And furthermore, challenges such as a limited laminar dataset and model generalization remain significant research gaps. Here it is three-class classification. They got a 93.7 for ResNet 50, and this is binary classification. This is four-class classification for bacterial pneumonia versus lung opacity versus normal versus COVID-19, and this is classification, three-class classification and convolutional neural network, and they got 95% accuracy. This is also four-class classification COVID-19, viral pneumonia, and bacterial pneumonia from healthy images. They got 89.89 percentage for convolutional neural network. This is binary classification. Again, the third three-class classification for COVID-19 and normal and pneumonia, they got a 93.37 percentage for ResNet 152. And these three are binary classifications. And the problem statement, despite the technological advancements, the current diagnostic methods suffer from several limitations. That is, they are time intensive and expensive. They rely heavily on expert radiologists, and malinterpretation is prone to human error and delays. Many AI systems lack multi-class classification probability. Therefore, this is a pressing need for a robust, automated, and cost-efficient system capable of accurately distinguishing between COVID-19 pneumonia and normal chest X-ray images. Then our primary objectives of this research are to design an automated diagnostic system using chest X-ray images and to implement and evaluate convolutional neural network, deep neural network, and transfer learning models to perform three-class classification, compare the model performance based on accuracy and efficiency, and develop a reliable and cost-effective clinical decision support tool. And the methodology involves the systematic pipeline. The images were pre-processed through resizing, normalization, and data splitting. Training and testing set for 80% and 20%. Three models were implemented: convolutional neural network, deep neural network, and transfer learning using VGG90. The models were trained and evaluated using TensorFlow, and the performance were adjusted using the standard deviation methods, especially accuracy. And the dataset description is this: a total of 817 images, COVID-19 pneumonia, and normal chest X-ray images. This is the architecture of CNN convolutional neural network. The CNN takes 224 into 224 into 3 RGB image as input and passes it to the network without computation. The first hidden layer has 3 convolutional 2D layers with a ReLU activation function to extract basic features like edges, followed by a max pooling layer to reduce size to 112 into 128, sorry, 64. And the second hidden layer increases the filter to 128 and learning more complex patterns and uses max pooling layer to further reduce dimensions. The third layer captures high-level features using 3 conventional 2D layers, and max pooling reduces the output to 28 into 28 into 128. And the flattened layer converts this into a one-dimensional vector, which is passed to the dense layer for learning future combinations. Finally, a softmax layer classifies the images into 3 classes and give the probability outputs. And this is the model accuracy and model loss. We have trained 140 epochs. And this is the parameter used for transfer learning. This model uses VGG90 as a feature extractor, where image features are converted into a 50,176 size vector. The last layer of VGG19 are frozen, so their learned features are preserved. These features are passed through the dense layers of 128, 256, 128, and 64 shapes with a ReLU activation function, followed by a dropout layer to reduce overfitting. And finally, a softmax layer classifies the input into 3 classes. All the models were implemented through using the TensorFlow framework, ensuring scalability and efficient computation. And training involved multiple epochs, that is 140 epochs, to optimize weights, and loss functions and optimizers were used to minimize classification error. And the training dataset was used to learn patterns and features. The testing dataset evaluated how well the model generalizes. Overfitting was controlled through the proper validation strategies, five-fold cross-validation, and multiple models were trained under the same dataset conditions. The performance were systematically compared. This enables identifications of the most suitable approach for real-world medical applications. We have got a CNN, the accuracy of 93.29%, DNN of 92.68%, and VGG19 transfer learning 97.56% of accuracy. Then this is the comparison with the state-of-the-art method, CNN plus CNN. They got 93.37%, CNN with AlexNet, VGG 16, and ResNet 50, 93.7%. Transfer learning, they got 94%, DNN 94.87%. TensorFlow based CNN 95%, CNN with ResNet 50, 96, CNN is 96, and ResNet 50, 92. Our LSTM with 90. VGG19 proposed model, we have got 97.56%. which outperforms the state-of-the-art method. Then the conclusion, the study validates the effectiveness of transfer learning, particularly the VGG19 model in medical image classification. The proposed system offers highly accurate, automated, and cost-effective diagnostic solutions, and especially beneficial for resource-constrained healthcare environments. This research contributes on advancing multi-class classification in medical imaging and supports the integration of AI in clinical decision making. Thank you.
Yeah, you have mentioned that you are using transfer learning, right? VGC19.
Yes, sir.
VGG19. Yes.
Yes, sir.
So how fine-tuning is performed?
This cross-validation we have performed, the networks we have changed, then freezing, after freezing the last layer of the VGG19, we have included the dense layer and the dropout layer.
Okay. So you're saying that the improvement is achieved over baseline methods.
Sorry?
So you're claiming that improvements achieved over baseline methods.
Yes, sir. Yes, sir.
Better than CNN and DNN. So model is highlighting the infected lung regions. Suppose if it is
sir.
detected.
Yes, sir.
Sure.
Yes, sir.
Okay. Thank you. Thank you.
Thanks. These are some of the references.
Okay.
Thank you so much for your presentation, Shailaja. So for today's last presentation, we have with us Lakshmi Priya Vijayan, who will be presenting her research work titled as Comparative Analysis of Efficient Deep Feature Extraction Strategies for Diabetic Eye Disease Classification. So Lakshmi Priya, are you ready?
Yes, ma'am. Yes.
Yes, you can start your presentation.
Okay. Am I visible, ma'am?
Yes, it is visible.
Okay. Okay, good afternoon, one and all. So today I'm here to present my topic, Comparative Analysis of Efficient Deep Feature Extraction Strategies for Diabetic Eye Disease Classification. So as an introduction, the early detection of diabetic eye diseases require accurate multi-class classification. Here, I am studying about the diabetic eye diseases and the relevance of the feature extraction for the various diabetic eye diseases on the basis of multi-class classification. The existing challenges for the feature extraction for the diabetic eye diseases are the CNN capture, local features, transformer, which is very efficient to capture the global dependencies, and the hybrid model. Both they combinedly they are defined something, but still now there are no such hybrid models to predicting for diabetic eye diseases for the multi-class classification. So in my work, I am just contributing a comparative analysis of the top 7 architectures focusing on effective feature extraction. Here the problem statement is like, currently the diabetic eye diseases prediction, multi-class prediction, it is limited inside, like existing studies is only focusing on the accuracy and it's not considering the feature learning mechanism. So this feature extraction gap is efficiently will be highlighting the result of the diabetic eye class disease prediction, and the research it's focusing there is no like presentation for the comparison of different deep feature extraction strategies will be existed. So my objective for with this paper is like, it's compare the top 7 deep learning feature extraction architectures, and here I am using 2 dual dataset evaluation is proposed, and the robustness is also analyzed with the help of this 2 dataset evaluation. Here the contributions are like, we are using 7 top based architectures, mostly in the CNN, transformer and hybrid, and also the attention based mechanism. And here I'm concentrated on 4-class classification, mainly for the diabetic eye diseases like diabetic retinopathy, cataract, glaucoma, and other categories. And here the performance analysis is based on the accuracy, precision, recall, and F1 score. And the practical insight for the contribution is like robust feature extraction strategy for automated retinal diagnosis. And the data set here I am using is like, from the Kaggle, I'm using 2 types of data set. First one, the ODAR data set, Ocular Disease Intelligent Recognition data set. And second one is the eye disease data set. Eye disease data set is actually, for the ODAR, the total, it will be contained like, for the normal, 2,873 images, for the glaucoma, 284, diabetic retinopathy 1608, and cataract 293 images. And for the eye disease data set, it's equally balanced. Like for the cataract, it is 1038 images, diabetic retinopathy 1098 images, glaucoma 1007 images, and normal 1074 images. So these are the most annotated data set which is available in the Kaggle. That's why I'm using these 2 data set for my study. And the main challenges which is I'm focusing here on my studies, like the class imbalances in some of my data set like ODIR, then the variability of image, like the resolution based on the resolution, angle, and the acquisition condition, and some noise and illumination challenges. So before moving to the in my work, I am just implementing all this by using the 2 data set. I am trying and implementing all this using the 7 architecture. So before moving to that, I am just do the pre-processing like image resizing with 128 into 128 format, normalization by using standard RGB mean and standard deviation. Then the data augmentation like rotation, flipping, and cropping was applied for the training set. And also for balancing the class imbalances, I'm just maintaining the class distribution across split by using stratified sampling. So these are the 7 models which I'm using. So the first one is the CNN convolution learned for the spatial features. It's actually good for spatial features, but it is more concentrating on the local features. Then VGG16 for transfer learning, pre-trained deep CNN. Then VIT, it's highly focused on the global attention. Then hybrid, like conformer, it's actually the combination of CNN and transformer. Then CNN VIT is also local plus global, but it's comparatively, when comparing with the conformer, it's less performance. Then CBAM. CBAM and SE I am supposed to use like it's for the attention mechanism, only concentrating like channel and spatial features. So these are the like architectures which I am try with my diabetic set. And the training setup I am configured like 30 epochs with batch size 16, and I'm using the ADAM optimizer with a learning rate of 3 into 10 raised to -4, and learning rate using the reduced LROP Plato with a patience of 3. And I'm also done a regularization of patient 6 to prevent the overfitting problems. Then the evaluation strategy for 5 independent runs and output layer is modified with the 4 annotated classification like diabetic retinopathy, glaucoma, then cataract or normal. And this is my results and discussion. So here the first one, the overall accuracy comparison with the evaluated models. So I'm already tried the 2 data set like ODIR 4-class and eye disease classification. In this, comparing to all others, the conformer model for the eye disease classification data set is much balanced. And for that, the conformer model will be get an accuracy with 91%. And also for ODIR, it will be achieved like 63. But the VGG16 is comparatively higher for the ODIR. But when we considering both the data set, the conformer model shown the much better result for this. Then here the class-wise performance analysis. When we compare with this, the ODIR data set is already it's some imbalance set, but it will classify the diabetic retinopathy and normal as much better way comparing to the eye disease. And the glaucoma and cataract will be having some problems occur like the due to its less size of the images. And I am here. I'm also using the GradCam visualization. So it's an using the explainable AI. It can be easily recognizing the most features for the 4 types of diabetic eye diseases, like diabetic retinopathy. The attention region will be clearly seen as in the lesion and microneums, and glaucoma. The optical disc region is also shown, and the cataract, the opacity areas is highlighted. And for the normal, the low scattered activation is available with this one. So by comparing, by using this GradCam also, the eye disease classification with the conformer, you get the much better result. And here, the computational complexity visualization. Here, when we comparing with the, here I am taking the most leading two ones like conformer and CNN VIT. For this, conformer get the less computational complexity when we compare with the other models. And this is the ablation study which I done for the attention mechanism. Here also, the conformer will be shown. It's high performance compared with the other architectures, and the statistical reliability across multiple runs. Here, I'm just taking 2 architectures, like the topmost 2 architectures, which I got the better result, like CNN VIT and conformer. Here, for each 4 classes, the conformer outperforms comparing to the other architecture. And the final concluding result is like the conformer achieve highest accuracy for the 4 data set, 4 diabetic eye class disease classification with approximately 91%, and CNN VIT with approximately 89%. So here I can conclude like, so by doing this study, by using the 7 architecture, I'm just evaluated with 2 data set. It's a fair comparative study, and the hybrid model like applying like combining CNN with transformer for improved feature learning, and the conformer achieve the most accuracy with a 91%. And this is the recommendation for the future study. Like in the coming study, I'm proposed for the like the future scope is like the model enhancement to improve the conformer architecture, the strong points of the conformer architecture for the advanced attention and multi-scale feature fusion, and also then extended validation for evaluate on large and more diverse clinical data sets. So these are my references. Thank you.
Thank
Your
you,
pre-processing
Lakshmi Priya.
steps are applied, right?
Yes, sir.
So did you perform the region of interest extraction?
Yes, sir.
Basically, yeah.
Yes, sir.
In which sense?
Sorry?
I mean, any format you have considered for region of interest extraction?
Actually, I'm done all the pre-processing like in a common standard step for the 2 data sets, sir.
So especially we are going for eye extraction, right?
Diabetic eye disease classification, sir.
So ROI extraction like optic disc or laser segmentation.
Sorry, sir.
This is performed. Optic disc or laser segmentation. This is
Yes,
performed.
lesion segmentation is performed actually, sir. Actually, my data set available from the Kaggle is already performed that lesion detection, lesion segmentation, sir. So by using that, I'm just do the resizing only.
Okay. And you have implemented the comparative criteria accuracy, right?
Yes, sir.
Any other criteria you have considered? I mean to say, if you're only considering accuracy, how you are ensuring the fair comparison across different models?
Yes, sir. I am done with the ablation study, and also I am just trying to implement this with both that data sets, sir. And here I am also done the GradCam for getting the correct predictions, to check out the is that a correct prediction or not, sir.
Also, you have mentioned you are preventing overfitting, right? By
Yes, sir. Yes, sir.
which
By
technique you
setting
are
the
using?
patient. Yes, sir. Regularization.
Regularization.
Yes.
Okay. Thank you.
Okay. Thank you, sir.
Okay, so this was the last presentation for today. So as we have come to the end of this session, I sincerely thank all our authors for their excellent presentations and valuable contributions, and all participants for being an important part of this international conference. I truly hope that this session was insightful, engaging, and inspiring for everybody. On behalf of the entire team, we thank you for your continued support, not just for this 11th edition, but for all our previous 10 editions of ICTIS. We look forward to welcoming you again in the 12th version in 2027. So, all presenters will receive their digital certificates via email within 2 working days, and the publication will be live within 7 to 8 months. So, we kindly request your cooperation with the ICTCIS team. So, I would like to extend my sincere thanks to our session chair, Dr. Virendra Kumar Thotre sir, for expertly chairing this session. So this is a small token of appreciation on behalf of the team ICTIS and Global Knowledge Research Foundation and partners. So thank you all once again for your valuable presence. And before we officially wrap up with this session, let us click a quick snapshot of this session. Uh, I kindly request everyone to switch on your cameras for that I can take a snapshot. So, wait, let me stop sharing the screen. Yeah, Shailaja, Sachin sir, I request everybody to please. Yeah. Yeah. Thank you, everyone. Take care. Stay safe, everyone. Thank you. Thank you, sir.
Thank you,
Thank you,
everyone. Thank you, all
Dhotre sir. Yeah.
participants. Thank you.